Hello everyone and welcome to another video of the Hidden Quantum Champions. Today we are going to explore a company called Quantum Machines, and with that let's hop right into it. Here I'm on their website and it says Quantum Machines, the new possible, introducing hybrid control, a revolutionary new approach for quantum developers to effortlessly achieve their ambitious milestones previously impossible. What do we see here? So there's a couple of known labels down here. So we see, for example, Alice and Bob, MIT, Pascal, Caltech, and so on. Then it says, go from unbearable friction to boundless achievement with hybrid control. There's far too much friction in our quantum R&D, and we are all feeling it. Slow progress, long run times, too high latencies. This happens when quantum control is disjointed. The quantum control units are poorly integrated with the needed classical compute, and the quantum operations run on a completely different thread from the classical ones. And the friction is only getting worse as qubits improve and scale. So, what are we looking at? Here we are looking at the interface between the quantum bit operation and the classical operation, especially in this NISQ era where the qubits, but also later on in the quantum error correction, where the qubits are still being run as physical qubits. We have the challenge that we need to deploy things like error mitigation. We have to fine tune, especially in the case of solid state qubits, like for example, superconducting qubits. And this needs a lot of feedback between the classical hardware, like the CPUs and the lab automation, and the new hardware, the qubits and the quantum control part. And I guess that's where the quantum machines come together, which is hybrid control. So hybrid control harmonizes quantum and classical operations, eliminating friction and optimizing performance across software and hardware so that builders can iterate at speed, resolve setbacks, and bring their visionary ideas to life. And then we have, for example, here Alice and Bob as a reference. Quantum Machines OPX played a key role in our roadmap. It enabled us to get the best control electronics out there, which is FPGAs, so field programmable gate arrays, without having to learn how to program them. QM provides QM is Quantum Machines, right? Provides a very scalable and very easy to use and very powerful hardware, which allows us to focus on the quantum science, says the CEO and co-founder Theo from Alice and Bob. Quick note on that. So FPGAs, what is that? An FPGA. So if you think about how your computer works on the inside, like your processor, for example, then you have these transistors that are running, for example, in the CPU. Now with specific tasks, there are also what is called ASICs. So there are like specific application processors that are very much tailored towards some very specific task. For example, if you're looking into video decoding, there are like specific building blocks, like little processors that are optimized to do this, I don't know, for example, color conversion or whatever, from the analog signal of the camera to a digital one, all of these types of things. Now these ASICs, they are very, very efficient, but they're only meant to be done for one, or only meant to be used for a specific task. Now with an FPGA, you can basically program an ASIC, so you have a building block where you can tune the different blocks to do one specific task, and you can program that. So that's why it's a field programmable gate array. These things, these FPGAs, they can do a lot of different tasks in a very efficient way, because you only program them maybe once to reassemble a specific layout, and then you can basically run this specific task on them, which is very interesting for this whole quantum optimization, because you can tune them in a way that, I don't know, they can be used for continuously calibrating, and then they can run on. And then as you understand the task better, you might change this into an ASIC or whatever. There's also some statement from Dirac. Dirac is delighted to partner with Quantum Machines and credits their OPX control system. I guess we will learn more about the OPX control system in a second, with its real-time capabilities as instrumental in achieving the results outlined in our research. The ease of programming sequence in the QUA significantly streamlined the experimental process. So that's also again a CEO, which is in disguise Andrew from Dirac. Okay, and there's more, but let's move on through the company here. So turn the impossible into possible. Hybrid control drives your entire product line, drives our entire product lineup. Discover how transformative it can be for your success. And then here we have the product, I guess. So what we see is again a rack-shaped unit, which probably fits into a standard rack. We also see there are a couple of channels here. So looks like coaxial connectors on here. 1, 2, 3, 4, 5, 6, 7, 8, and there's another 2 here. And this might also be some connectors. Looks a little bit like a radio frequency plug, but maybe it's not. I don't know. It's hard to say. And there are different units here. So this one has a different layout from this one. And I guess we will learn more about these 2 different units in a second. So the pulse processing unit, PPU. The PPU delivers classical computing that operates as close to qubits as possible, minimizing overhead and ensuring rapid, comprehensive, and frictional operations. So active reset latency is 160 nanoseconds. It operates, so controlled GPU round trip latency is below 4 microseconds, and then it's over 97% XEB QPU utilization. And I'm not an expert for this again. I'm just reading the numbers here, right? If I read pulse processing unit, sorry, I need to hydrate quickly. I'm thinking about microwave pulses, for example, that go down into, I don't know, a superconducting qubit system to control the operation of a qubit. But let's see what else we can learn here. So the hybrid development platform. Built on the QUA language, the hybrid controller lets you program and run quantum and classical operations using intuitive code, making it easy to tackle even the most complex tasks. And what we see here looks very much like a Python environment to me, where you basically set up the different settings up here, and then you have a qubit in there, there's a resonator, a readout. So various different operations, and then you have play, you have measure, assign, and so on. Intuitive frictionless development, write quantum and classical operations in, I think there's a space missing, complete unison with a highly flexible and expressive language, accelerated development, ready to use community-supported QUA protocols to simplify experimentation and speed up quantum workflows, and then the control stack compatibility, integrate any stack and language smoothly into a hybrid architecture, including OpenQASM, Qiskit, and QDAQ. Okay, then what do we have here? Achieve record fidelity at scale with the qubit-led analog front end. So what do we have here? We work backward from qubit requirements to design a classical analog front end that delivers outstanding performance and specs, creating a control system that is never a bottleneck for performance. So optimized gate fidelities get the most out of every operation with analog excellence, delivering state-of-the-art SFDR, THD, crosstalk, phase coherence, etc., and then built for scaling that makes economic sense, delivering the industry's highest channel density with outstanding end-to-end performance and scalable cost. So here it says 99.99% gate fidelity enabled by, I think there's again missing space, 150 femtoseconds integrated jitter, more than 150 dB decibel SNR, signal to noise ratio at 10 dBm magnitude, right? Output power for strongest drive at lowest noise, and then there's 75 dBc SFDR across the full operations range. Okay, then we see here some quotes from different people again, from different institutions. And then what do you want to achieve? Build quantum computers, research and experimentation. Then there's some more to learn down here about superconducting. And I think these are probably now the qubit architectures that are being used, right? Superconducting and quantum dots. There's also neutral atoms, and then defect centers and optically addressable systems. So these are 4 different qubit technologies that are probably target for this type of for the quantum machines hardware. Discover our hybrid control product line. Every product is crafted with unparalleled engineering excellence. So here we see all the different products. We have the modular high-density hybrid control platform, the PPU-based direct signal synthesis hybrid control and readout module from 50 MHz to 10.5 GHz, which basically is relevant for the gigahertz frequency are usually relevant for the control mechanisms of, I don't know, for example, spin qubits or superconducting qubits, and then you can go down here in the frequency to probably do operations, read out, whatever. Then we see the PPU-based low-frequency hybrid control and readout module DC up to 750 MHz. This is maybe for stabilizing voltages, keeping gates at a specific voltage, but then also doing some drives of gates. But it's the lower frequency range here, because it starts from DC, so basically stable currents, right? Then there's the PPU-based ultra-fast hybrid controller, an up-down conversion up to 18 GHz. So you can basically take probably the signals that you get from this one here, and then you can use this octave device here to basically double the frequency. So you can go up to 18, which is 9 GHz input signal will then be upsampled to 18 GHz output signal. And then you have this high density ultra low noise DAC, which is another important component that you need when you have, let's say, a lot of gates that you want to tune. There's the QDAC2 ultra low noise DAC. There's a Q switch, so software controlled breakout box. That is relevant if you, for example, have, let's say you have 150 qubits, then you might not have 150 devices that are measuring these qubits all the time. So that's when you usually want to have these switches here where you connect one instrument and then you can switch between, in this case, I think it's 8 different channels. That way you might have a big matrix box or a DAC which outputs all the different channels outside your cryostat, and then you can switch the input instruments to all the output panels. That's what you also see in the typical lab setup. And then there's also cryogenic control systems here, high fidelity with minimum losses, cryogenic sample holders, and multi-stage filters. So here you see a typical holder. That's where the quantum chip goes inside. This is called the cold finger, or the coldest part of the cryostat, right? And then you see there's all the signal lines connecting up from there. And usually those signal lines, they don't just go straight all the way up to the room temperature stage, but usually in between you have different filter stages that are filtering out noise, but also thermal noise. So if you, for example, think about electrons, they are distributed at room temperature. It's a statistical distribution of the energy levels of the electrons around the Fermi level. So the Fermi level is where, if you have a cold system which is fully occupied with electrons, that's where the electronic energy would reside. So the maximum level that the electrons would sit at. And now as you warm up the system, you will have electrons that will take this thermal energy and convert it into electronic energy. So you have random movement of electrons. And if you come from room temperature and you want to cool down a system, then you want to have these random electron movements basically filtered out. So you need to have a filter which is at lower temperature. And this is these filter stages here. Okay. And then what else do we have? Dive into the world of quantum machines. So there's like some scientific publications, blog and seminar also available from them. And then there's also a request for a demo here. Okay, so let's go all the way up again and see what else we find here. So there's information on the products that we've just seen, which are separated into control hardware and software. So there's control software as well. Then here we have something that is more solutions oriented. Again, what we saw before, there's like these 4 different qubit types here: superconducting, semiconductor spin qubits, optically addressable, and then neutral atoms. So like these ones, they are, for example, diamond and V centers, whatever. And then we have the neutral atoms here as well that are optically manipulated. But then on the other hand, we also have the use cases. So quantum research, quantum computing at scale, quantum for HPCs or high performance compute, quantum control for transducers, quantum sensing, and quantum networking or quantum networks. So we have the communication, the sensing, and then the quantum compute. And then there's also the research stack here. Then there's something about the technology, so the PPU that we've seen before. Then there's also the control benchmarks here, ultra-fast feedback, and direct digital synthesis. There's a partner program as well. And we will see also what this includes later on. There's the resource center with scientific publications, a blog, some brochures. They even have a podcast here and videos and an FAQ. So in this case, there's no glossary, but we have a lot of other stuff, like for example, a podcast and videos available. And then the last one is about the company itself. And we will of course check also this part out in a later stage of this video. But now let's quickly take a look at the products again. So I think we have seen like a brief going through all of these before, but now let's maybe check out the first one, which is the OPX1000 modular high density hybrid control platform. That's something that we've seen already in a picture before. Let's quickly go through it and see what it actually is. So overview. Trusted by the builders of the world's most advanced quantum computers, OPX1000 is the industry's leading hybrid control platform, delivering unmatched agility, flexibility, and ease of use while supporting all quantum processor modalities. Powered by Quantum Machines' unique pulse processing units, PPUs, and we will look at those later, the OPX1000 brings classical resources as close as possible to the qubits, eliminating latencies, enabling real-time adaptive protocols, and accelerating quantum breakthroughs. With OPX1000, quantum computer builders can seamlessly scale systems, push the boundaries of quantum classical integration, and unlock new possibilities previously impossible. Then there's also a video here. Let's quickly check out the microwave module. So this is one part, I guess, of this box. Modular with any combination of low frequency and microwave modules and any number of OPX1000 units programmed together and operating as one. Unmatched real-time processing power and the fastest feedback, and then highest channel density in the industry, so 80 analog channels, 3U, cutting-edge analog front-end scale, and then unison quantum and classical programming in a comprehensive, easy-to-learn hybrid development platform. There's the low-frequency module as well. Oh, not sure. Oh, okay. Don't know what this is doing. There's oh, maybe I just have to scroll down. So there's the microwave front end. We've seen that. It goes up to 10 gigahertz. It has 2 analog inputs, which also go up to 10 gigahertz. There's digital markers. What else do we have here? Jitter information, phase noise, active reset. Okay, so quite a lot of information. There's also a spec sheet. Then there's this low frequency front-end module. We also saw that one before. that comes also with a very low voltage noise of less than 30 nanovolt per square root hertz at 100 kilohertz though. It has a rise time of less than 500 picoseconds at 0.8 VPP step. And okay, it also comes with 2 analog inputs as the other one and 8 analog outputs in this case. And it has 16 cores of the PPU. And again, we will check this one out later. There's also some, examples here. And I think we've seen these ones before, like case studies or people that have been using this. Then there's again some information on the PPU, but we will check out the dedicated page later on. Smooth scalability, so you can apparently connect these pretty well and you can use multiple of these in the same setup. It says things like automatic synchronization. I think that's really meant to be used for scaling. And then again, we see this hybrid programming here with the QUA, an open source pulse level programming language. So that's basically probably used for the pulse shaping and the readout and so on. Then we have GPU-powered hybrid control. So the OPX1000 redefines hybrid quantum classical computing with seamless GPU acceleration, delivering data transfer speeds of up to 1,000 times faster than other controllers. Through NVIDIA DGX Quantum, it establishes an ultra-fast link between the PPU and the GPUs and CPUs, enabling tightly synchronized hybrid algorithms that push the boundaries of large-scale quantum computing. By eliminating bottlenecks between quantum control and classical processing, OPX1000 unblocks real-time quantum error correction, accelerated calibration, and next-generation hybrid algorithms, all with minimal latency and maximum efficiency. So the benefits are achieving milestones faster and unlock the new possible, achieve record fidelities at scale, HPC and QC deep integration, smooth scale, high uptime, and future-proof. Okay, and then there's some more information down here. Your experiments reside in a phase space. OPX1000, the only controller covering this space in real time. And then we see here, so we can we have a fully parametric waveform generation. So that's what I was mentioning before, right? Like the waveform generator, like arbitrary waveform generator. You can see here loop over parameters in real time, durations, frequency, phase, amplitude, bandwidth, real time. So you can basically create a pulse shape here or like a wave shape here. Wave acquisition and manipulation, high resolution analog to digital conversion, user-defined flexible integration and demodulation, high tagging and TTL counting. And then you have here real-time processing, arithmetic and trigonometric functions, vector operations, casting of variable types, Bayesian, and so on. And then there's also this part here, comprehensive control flow, if-else loops, while loops, for loops, and switching. Now, why is all of this important? So if you, for example, think about the pulse shapes, right? We are talking about 10 gigahertz here. So this is like quite a high number. It's not like easy to analyze signal, right? You have like when you create those signals and you also want to read them out, that generates a lot of data. We are looking at very high sampling rates here, at very and this is like a continuous process, right? Because you're writing into your qubit and you're reading out the qubit. So this is like continuously going on at pretty high rates. Now, this means if you want to drive this from your computer, you will have a lot of data going back and forth constantly. And I mean, you can do that for 1 qubit or for 2 qubits, but if you really want to scale things up, then you actually need to move the compute, so the analysis of the signal and also the generation of the signal, closer to the actual quantum computer and away from your classical computer that is controlling the setup, because otherwise you have too much data going back and forth. So that's, I think, what this whole story here is about the pulse processing unit, because if you go up to 10 gigahertz, here what you can do is you can first of all, you tell the system which signal you want to send. So instead of, let's say, sending the signal from your computer, you basically tell it, I want to have a pulse at, I don't know, 7 gigahertz, which has this duration, this amplitude, and so on. And then it will be generated. As we saw before, these units are synced automatically. So that's all kind of in a uniform time frame. So the readout knows when the process unit or the processor is sending something. And then you can also do some analysis here already. And that's also very important. So you can basically look at what you put in and what you get out. You can do some easy logics with that here, right? You have if-else statement, for loops, while loops, and so on. So you can basically shift all the tasks to the box. Then it probably automatically runs through all of the different tasks. It reads out the signal, compares everything, and then sends you back the metadata. Like, for example, is your qubit in the state 1 or 0? Because technically what you will read out from a superconducting qubit or a semiconductor qubit is not like, is it 1 or 0? You will get some voltage data or some current data, and then you have to transform this back into the actual information. Okay, is my qubit at 1 or 0, right? And there's many stages in between. You have filters sitting in there and all of that stuff. Like the signals that you generate, they are also not just 1 or 0, they are high frequency signals. So all of this kind of can be condensed down and probably be processed here so that you end up with, let's say, less data flow back and forth. And some of the intelligence goes into the PPU. Okay, let's also quickly check this out in one of these cases here. So let's look at maybe this time semiconductor spin qubits, because why not? So here we see a nice picture of the qubits. There are spins pointing up and down. Here we see the different gates manipulating them. And it says quantum control for semiconductor spin qubits, a high performance, fully integrated and scalable control solution for the most advanced semiconductor spin qubit processors. Here we then see the solution. So this is the sample holders, some filters here. I think these are QDevil filters. And then we have the quantum machines set up here. Now, what I'm now wondering is, like, QDevil, are they working in a collaboration, or did they actually buy the company? Because I remember in my PhD times there was still QDevil as a separate entity, but I don't know. Let's see. Ultra-fast quantum operations run complex spin qubit algorithms with real-time feedback and unmatched classical processing, unlocking previously impossible protocols, from state-of-the-art cryogenic sample holders and filters to room temperature controllers. With unmatched capabilities, we have got you covered. Cutting-edge electronics, ultra-low jitter, minimal noise and phase noise, ultra-stable DAC, resolution and noise, highest spin qubit fidelity, demonstrated electron temperatures as low as 22 millikelvin. That's what I was referring to before, right? Like when you look at your Fermi energy and how scattered your electrons are, you can basically take this and calculate more or less the electron temperature from that. In a cryostat, you reach physical temperatures down to these 20 millikelvin. And here they also show that, like, the electron temperature really goes down to this value. Then there's accelerated QPU tune-up, modular video mode architecture for dynamic, rapid tuning of QPU parameters. And then we have the unmatched support from quantum machines. Experienced experimental physicists with a deep understanding of use cases will help you bring up your system, train your team, and solve challenges. And then here's also some explanation on the specific spin qubit architecture, I would assume. So control suite for spin qubits. Here you see which products you need and how they are actually set up with the system. Initialize the semiconductor device. So here I think it explains the tuning. The tuning is the next step. Tuning to the single electron regime. Expediting tune-up. Then we have spin qubit characterization, starter kit, advanced characterization, and beyond, where you analyze how your system actually works, like fidelity and so on. Then suppressing qubit dephasing with real-time Hamiltonian estimation. So this is now this not quantum error correction, but error suppression schemes, or how to remove errors or keep errors low by tuning stuff. And then, yeah, there are some references down here. So this is almost like a thesis work on how to work with a semiconductor spin qubit system. Very helpful, I guess. I haven't looked into the details though yet. Run the most complex quantum experiments out of the box. Then there are some different pointers here to different topics. And again, down here we see the different products. Okay, so let's not stretch it for too long today. Let's also very briefly check out this one. Again, there's a lot of text here explaining what high performance actually means, DGX quantum, so OPX and the grasshopper in the same architecture, so what they do with NVIDIA, maximum quantum utilization, long-term operation, so this is really meant to operate in a server center, I guess, or in a data center. Okay, but I don't want to go into the details too much here for today because I also wanted to quickly check out the technology, so the PPU that we've seen before, which is like the FPGA-based pulse shaping unit, I guess. So the pulse processing unit, PPU, is an advanced classical processor central to quantum machines' hybrid control approach. By positioning classical computer resources as close as possible to the quantum hardware, the PPU enables real-time execution of quantum control protocols with minimal overhead, ensuring rapid, comprehensive, and frictional operation. Built into the OPX 1000 front-end module and the OPX Plus system, multiple PPUs operate as one, orchestrating control, readout, and calculations, handling data sharing and synchronization. And that's what we discussed before, right? So we have unmatched real-time operation capabilities, unique external acceleration, easy as pseudo coding. PPUs are programmed via QUA, an open source programming language designed specifically to combine quantum control with classical computation and intuitive control flow. QUA provides pulse level programming while remaining super easy to use and understand as pseudocoding. QUA is central to Quantum Machine's hybrid development platform, which includes a comprehensive library for easy to use control applications that significantly reduce development time. As part of this platform, QUA programs can be seamlessly integrated and controlled using QUA Liberate Quantum Machines automated, scalable calibration solutions for quantum computers powered by OPX hybrid controllers. And here we see the QUA and the QUA Liberate, Qiskit as a quantum computing programming interface, as well as CUDA-Q from NVIDIA and the OpenQASM 3. And then again, there's some of the benefits down here. Okay, so seems like, okay, the base technology is really this chip, and I don't know if there's like very lot explanation here of how that works in the details. Let's see, digital wave, direct digital synthesis, DDS. Okay, here we see how that would be integrated. So you have the quantum control stack sitting here with the OPX 1000 and then the quantum processor with up to 1000 superconducting qubits. And then there are servers here. So this is what like the hybrid quantum and classical compute server center might look like. DDS with alternative solutions, okay, and then there are some additional resources here. But I don't want to go into the details at this point too much, because otherwise it will get too long. But I mean, if you want me to do so, let me know down in the comments below, and then I will check out everything else here as well. Let's quickly see what they have in the partner program. So here it says QM partner program. We are proud to partner with global leaders in quantum computing and HPC. Join us. Here's the companies that they are partnering with. So we see NVIDIA, Oxford Instruments, Rigetti, there's Applied Materials, Toyota, Qera, Blue Force as a Christad company, QRISE, Partec, Quantrol Ox, Classique, Quantware, and so on. So the list is very long. So then you have Conscience, Track, Riverlane, Entropica Labs, Quantum Elements, and Zero Point Cryogenics as the partners listed on here. So various different partners from various different areas. We have NVIDIA, which everyone knows, right? Then there's Rigetti as, for example, a superconducting quantum computing system manufacturer. We have Oxford as, let's say, an enabler. Oxford Instruments as an enabler for quantum systems, but then also Toyota is probably one of the users of those. Then we have Bluefors as a cryostat manufacturer, Classic, who is more on the algorithm side of things. So this is a real ecosystem forming here in this partner program. Now let's quickly, as a last thing, check out the About Us section, as we always do at the end. So Quantum Machines team, sparking a new era in quantum. We are a team of quantum physicists, software and system engineers, and chip designers, all passionate to advance the world of quantum further than it has ever gone before. We envision a new technological age, a time when quantum computing is used to revolutionize entire industries, solve global problems, and power unprecedented innovation. That's why we made it our mission to build quantum orchestration, a platform that powers quantum breakthroughs and accelerates the path towards the new age of quantum computing. And then here we see the co-founders and I guess the VP board and the C-level executives. Then there are also some board members here. We see the different investors. Qualcomm is, for example, a very well-known chip manufacturer. Then we have Intel, which is a very well-known chip investor. There's Samsung in there as well, so a lot of big names. They also have open positions. You see they have various different locations here. So there's USA, Israel, Denmark, there's Germany, France, and Japan. So all around the world. And with that, I think I will close today's little overview over quantum machines. If you liked it, please make sure to give it a thumbs up, and then see you in the next one. Bye bye.